welcome back to Decaf-Math ASMR, and a warm welcome if you are new here. I hope that you are doing well and that you are ready to relax with some math together. We don't often hear those words together, relax and math, but I do hope that this video is helpful, especially if you are learning this stuff or are interested in it. And I hope that it is encouraging and calming and really whatever you need it to be. Maybe it's just boring enough to help you drift off to sleep. Promise I won't get upset. Feel free to drift off to sleep. So today we will be going over another requested topic, and that is partial P-A-R-T-I-A-L fraction F-R-A-C-T-I-O-N decomposition. And I hope that it is tingly, relax, tingly, and relaxing. And I've gotten a few requests for this actually in different contexts. I think the most common application of partial fraction decompositions is actually in calculus when finding integrals. So it's a tool that we can use when we're finding the integral of something over something. So a rational expression. And so sometimes substitution doesn't work, or integration by parts doesn't work, and you're just left with this awkward integral to find, and you don't really know what to do. And sometimes you can use this technique of partial fraction decomposition to break your fraction into the sum of smaller fractions, and sometimes the integrals of those pieces are easier to work with. So sometimes it leaves you with the natural log, or sometimes you can use u sub or integration by parts or something like that. So the technique itself, though, is based on algebra. So you don't really need anything past algebra to be able to carry it out. But oftentimes it's kind of introduced with calculus. So today we are going to focus on the actual decomposition part, and we can come back to this kind of practice another time. That's okay, since that just involves more practice with integration. So This part can be kind of tedious, but it's kind of like how algebra can be a little tedious sometimes, but it kind of just works out. So I want to kind of take it step by step, and today I wanted to focus on linear factors. But before we do that, let's kind of review how fractions go. So let's say I have 1 over x plus 1 plus 2 over x plus 3. So I have a fraction plus another fraction. If I were to combine them into one, and this works for arithmetic, like 1 over 2 plus 2 over 7 or something. But when we add, we don't just do 1 plus 2 is 3, and then x plus 1 plus x plus 2 is 2x plus 4. We do not do that. We actually find a common denominator. The least common denominator makes it easier. In this case, since I have an x plus 1 and an x plus 3, then a common denominator of x plus 1 times x plus 3 makes the most sense. And so what you do is we take this first part and we see we have an x plus 1 already on the bottom. So to make it have this common denominator, I just need another piece of x plus 3. So I just multiply by x plus 3 on the bottom and on the top, just to make sure it stays an equivalent fraction, so to speak. So we're basically rewriting this as an equivalent fraction. So x plus 3 times 1 is just going to be x plus 3. And then the bottom's the x plus 3 times x plus 1. And so that's going to be an equivalent fraction, because x plus 3 divided by itself, it's just 1, and that goes away, because 1 times anything is itself. So x plus 3 over x plus 3 times x plus 1 is the same thing as 1 over x plus 1. So we'll do the same thing on this side for this piece. X plus 3 just is missing an x plus 1 for this common denominator. So I'll go ahead and multiply by x plus 1 on the top and on the bottom. So on the bottom we have the same common denominator. So when we add, we keep that same denominator. And then on the top we have a plus 2 times x plus 1. If you need an intermediate step here to write the two equivalent fractions separately, that's okay. And then you smush them together on the top and keep the bottom. But we did it in one step here, which is fine. And then you just go ahead and you distribute this to the x plus 3 just stays the same. Parentheses can go away. So this is the 2x plus 2. And then you add like terms. So you end up getting 3x plus 5 over. And then you could actually FOIL this out. First terms multiplied to give you x squared. Outer terms are 3x, inner is x, so that's a 4x. And then last would be 1 times 3. And I'm not going into much detail with that because we've kind of covered it here on this channel, but also because I feel like by the time you do partial fraction decomposition, this stuff kind of should hopefully look familiar. But don't stress yourself if it doesn't. But my point is basically that this is the opposite of partial fraction decomposition. We basically took two parts and we made it into one thing here. And so the decomposition is the other way. We start with something like this and we try to break it down into kind of these smaller pieces. And that's all that it is. And there's pretty much a systematic approach to it. And, I'm not much for rules, so to speak, in math. Just the logic, because in the long run it's pretty much impossible to memorize every single thing. But there are some techniques and tricks for this, so we'll just want to be clear with the scenarios that we're working with. And today we're going to focus on linear factors, but let's just kind of go over the general words that we might kind of come across. So if you notice in this case, if we were to break this up into the two, the bottom here, x plus 1 and x plus 3, those are linear factors. Linear factors. And they're just singular, so x plus 1 and x plus 3. But in general, that would just be anything of the form, ax plus b, where a and b are numbers. So no square roots, no powers other than the secret power of 1, right? X to the 1 is just x. So, x minus 1, it could be like 3x plus 4, negative, half x. I don't know, I'm just trying to cover my bases here. Plus 10. But as long as the variable's x and there's no other power except for just x alone, that's a linear factor. So x plus 1, here a would be 1, b would be 1, x plus 3 is linear as well. And so quadratic factors, like the quadratic equation, have the form ax squared plus bx plus c, where a, b, and c are numbers and can be 0. But the idea is that you have this x squared term. That's what makes it a quadratic and possibly a linear part of it. But here when we broke this one down, we have just linear pieces, but sometimes you're going to deal with quadratic. So that could just be x squared alone. It could be 3x squared minus 5, even when b is 0, that's okay. X squared, minus 2x plus 3, that kind of stuff, as long as there's an x squared term. And then we have the idea of repeated linear and repeated quadratic. And those are pretty much the different situations that we use for this kind of stuff. Then it gets really ridiculously tedious. But for repeated linear, that just means taking a linear factor and raising it to a power. So like x plus 1 squared or something like that. And for quadratic, x squared minus 3x to the power of 2. Usually 2 is as complicated as you'll use, but that's the idea of repeated. So these are just not repeated. So today, lots of wording and terminology, but really the only reason we need to even pay attention to this kind of wording is to help us decide what we need to put in the numerator as we solve this. So it's more like a grouping of methods more than the actual wording itself. It's not that important actually, but just kind of helps us keep track of what method we're going to do. So for now, today we're going to look at linear factors that are not repeated. And this is an example of that because our bottom have linear factors and there's no squared or anything like that. So let's look at how to go from here to something like this. So I'm going to use the pack here because I don't want to waste all this paper. But so let's just change the numbers a little bit just to keep it fresh. Let's say we have 3x plus 7 all over x squared plus 5x plus 6. So you'll notice that this has a very similar form as the last situation. So the first thing to do in the decomposition is it's helpful to try to factor the bottom. So let's just go ahead and start with that. So this bottom thing, if we can factor it, in this case we can. And again, this is assuming we're pretty comfortable with factoring. So we're looking for two numbers that multiply to be 6 and it's a plus. So either both numbers are going to be a negative or both are going to be positive so that they multiply to give me 6. And we also want to keep track of the outer and the inner adding to be 5x. So 2 times 3 is 6 and 2 plus 3 is 5. So that's how we're going to factor this bottom. And you can check that by foiling it back out and it'll become this. So the first step is to factor the bottom to see what's going on. And then we see that once it's completely factored out, we actually have these linear factors. So that's how you can determine what situation you're working with. So in this case, our bottom has a linear factor here and a linear factor here. So we're going to split this up, right? We're going to try to split this thingy up into the two parts, something plus something. So we're kind of going to work backwards here. We're going to have one piece that's an x plus 2, and the other piece is going to be our x plus 3. Okay, so just, it's the opposite of finding our common denominator. And whenever I have this linear factor like this and this, I'm just going to put an a here and a b here. These are the variables that we're actually going to solve for, and they are placeholders for numbers. So whenever it's just a linear factor, you just put a constant a and a constant b. Okay? And so our goal is to determine what the values of a and b are. So now we're just going to work backwards to try and figure out what a and b have to be so that this works out to be 3x plus 7. There's a few ways to do this, but the factoring part of the denominator gives you a sense of what form a and b have to be. So there's slightly different rules for today's stuff. Just because they're linear and not repeated, we can just put constants a and b. So at this point, you can kind of work through the same, going back now to combine the common denominator and do a times now's the part where it's just all algebra based and based on your preference. So one way to do it is to just write it out. So you would do what we did before, which is basically just multiply this by x plus 3 over x plus 3, and this by x plus 2 over x plus 2, so that you get something of this form, so that we would have a times x plus 3 plus b times x plus 2 equals 3x plus 7. The bottom part takes care of itself because that's the point of breaking it down. So we just need to solve for what a and b are. So in other words, we just add these back together and we set it equal to the numerator. But that's the exact same thing as actually multiplying this whole thing by x plus 2 times x plus 3, and this whole thing by x plus 2 times x plus 3. So it's like multiplying both sides of an equal sign. This equal sign. So if you multiply this whole thing, that just cancels out the bottom. And for this part, you distribute it. So for this one, you're canceling out the x plus 2 and leaving an x plus 3. And for this piece, you're canceling out the x plus 3 and leaving an x plus 2. Either way, you're left with this sort of equation to work with to get a and b. So from here, there are kind of two ways that fall out of this to solve for a and b. One is to make a system of linear equations where basically if I distribute this out, I'll do it really quick, but if I have ax plus 3a plus bx plus 2b, and that equals 3x plus 7, then you know that the coefficients here, a and b in front of x, have to add to be 3. So you have a plus b equals 3, and at the same time, 3a plus 2b must equal 7. Like so. And so that's a system of equations, and you can solve this however you want to, right? You have two variables and two equations. So you can do substitution, you can do the thing where you eliminate one, whatever, however you want to solve those, that's fine. As long as they solve these two simultaneously. But another way to do this is actually this little trick where you substitute convenient values for x to help you eliminate 1. So let me show you an example of that. So in this case, if we were to say this side always equals this side, whatever my a and b is, it should satisfy always, no matter what x values I put into this, and this, and as long as they're the same number. And so I may as well pick nice ones, and by nice I mean, let's say I plug in x equals -3, okay, into this. If x is -3, this goes away, because -3 plus 3 is 0, and 0 times anything goes away. So that's kind of nice. So this is going to be -3. So b times -3 plus 2, I have to put it into every x, equals 3 times -3 plus 7. So then -3 plus 2 is -1, so that's -b equals -9. 3 times -3 is -9, plus 7 is -2. And then dividing by -1 on both sides means b equals +2. So that's another way to do it. And then to solve for a, you can either substitute this in, or you can just do the same trick and set x equals -2. because that'll make this go away now. And I have a times negative 2 plus 3 equals 3 times negative 2 plus 7. And that's negative 6 plus 7, so that's 1. And negative 2 plus 3 is 1, so a equals 1. And you can also kind of do half of this method and half of this method, get b is 2, and then say a plus 2 is 3, so you subtract 2, so a equals 1. That kind of thing. Really just by whatever means you can solve for a and b simultaneously. But this way involves kind of solving it in general and then setting the coefficients to line up. That's all. That's all. But either way, we get a equals 1 and b equals 2, conveniently. And so we just plug it right back in. So our answer for this decomposition would be that 3x plus 7 over x squared plus 5x plus 6 would be 1 over x plus 2 plus 2 over x plus 3, like so. And the nice thing about this is you can always just check. So you can do what we did on this other page here and just check by adding it, finding the common denominators and adding. So hopefully if we got the right numbers, it should equal this. Okay, cool. So let's just work out another one. Let's say we have 6x squared plus 29x minus 40 all over x squared plus 3x squared minus 10x. And I actually just made up these questions. I mean, I can't say that they don't exist anywhere ever, but I just made up these numbers and stuff, and hopefully they work. So again, there's of course lots of ways to do this, but I just wanted to make a point here that factoring the bottom can be helpful. Again, just factor it however you can. Oops, I meant this to be x cubed, by the way. X cubed plus 3x squared minus 10x. That way, I can factor out an x here, and I would have x squared. So if I factored from this bottom an x squared plus 3x minus 10, then I would have, what two numbers multiply to give me negative 10, but add to give me 3. That would be an x minus 2 times x plus 5, like so. And then just leave the top as is. Nice. So I'm moving a little bit quicker through this one just because it's tedious again, but we also kind of did an example before this. But here's an example of 3 factors. 1, 2, 3 linear factors. So no squares out here, so nothing repeated, and no quadratics on the inside. So these are just 3 linear factors, which means we are going to go ahead again, have parts like this just for each factor. And in this case, I picked this question to do because I wanted an example of 3 factors. So sometimes it's 2, sometimes it's 3. It just depends on how many factors and what types. So in this case, we have 3 linear factors. And so anytime we have a linear factor, we just put in a letter and a constant, like so. And then we want to solve this. So we want to make sure that when we combine this back together, we get the top, the numerator that we're looking for. So when you do this, again, you can just think of it as multiplying by x times x minus 2 times x plus 5 on both sides, like that whole denominator on both sides of this equal sign. So it actually ends up just pretty much working out to be just looking for whichever pieces you don't have. So when I distribute this like this, I see that I'm basically this 6x squared plus 29x minus 40 is just left there because this whole denominator is being multiplied. So those cancel. So on the top, I'm going to be left with, for this piece, I just need a times the other two factors, because x and x will cancel, but you still have an x minus 2 times x plus 5 plus b times, for this piece, you're just missing an x and an x plus 5, so the x minus 2 parts cancel. So bx times x plus 5 plus c, and then for this piece you have x and x minus 2 missing, like so. And then this whole mess is going to equal 6x squared plus 29x minus 40. I wasn't kidding when I said this could get tedious, but the method is still exactly the same. You just expand it out and let the top equal the other top, and now we just need to solve. So you can just do it. First is x squared, outer is 5x, inner is minus 2x, so plus 3x minus 10 plus, then distribute this, bx squared plus 5bx plus cx squared, cx squared minus 2cx. Again, you can do it this way where you then expand the a out, and then you set a plus b plus c is 6, so you can have a system of linear equations again if you want, whichever way is easier for you. But and then like 3a plus 5b minus 2c, because those are the coefficients of the x terms, will be equal to 29, and then negative 10a will be negative 40. So you can do it that way. So you just have three equations, blah, blah, and blah, and then solve them however you can. Substitution or whatever, elimination. But we can also try this other thingy where we try to pick pretty convenient numbers, so again, we want the pieces to go away, but since this is an equation and it should always satisfy no matter what x values you pick, you might as well pick convenient ones. So one way to do that is to set x equal 0. That's nice because then this and this would go away. So if I plug in 0 throughout every single x in this equation, I have 6 times 0 squared is 0 plus 0. So you have negative 40 equals a times 0 minus 2 is negative 2 times 5. And then this will be 0 and this will be 0. So negative 40 equals negative 10a. And so if I divide by negative 10 on both sides, I get a equals 4. So that's a nice start. So if we already have a is 4, then we can just put that in. And then we can pick what happens when x equals 2. So then this part will go away and this part will go away, which is kind of nice. So we'll just say x equals 2. We would have 6 times 4, because that's 2 squared, plus 58 minus 40 equals, this goes away because of the x minus 2, b times 2 times 7. So whatever that is, 14b. So that would be 42 is 14b, so you divide by 14 on both sides, so that's 3. So b is 3. And then you can do, x equals -5, just to round it off. Or at this point, since I already wrote the first line of the coefficients here, I know that a plus b and plus c has to be 6. So instead of plugging and chugging that in, I can go ahead and just, if I have 4 plus 3 plus c is -6, then c, or positive 6, sorry. Then I have 7 plus c equals 6, and c equals 6 minus 7, which is -1. So c equals -1, kind of trusting our process here. But then you just go ahead and plug it in. So 4, 3, -1. And if you have a -1 up here, a plus -1, you can just put the minus over to the side. So our answer for the decomposition is going to be 4 over x. And make sure you're putting a, b, and c properly, because it has to correspond to the right factor. So then -1 over x plus 5. And that is the decomposition. Oh, hopefully we got that right. I'll probably end up multiplying this out and checking it just to make sure we got the right answer for this, but that is the general method. So again, in this case, you can just do it however you need to do it to solve for a, b, and c. So I kind of combined expanding everything out and drawing corresponding coefficients to what we're looking for, and writing a system of equations that way, and picking convenient ones. But you could just stick with one method or the other. Just, you would have to plug in x equals -5 for this last bit here, and this part and this part will go away, so you could solve c this way. It's just kind of tedious is all. So yeah, so that is the nice thing. Again, you can just go back and add it back together, make sure it all works out to be what you were looking for. And so this is the case for linear factors that don't repeat. So we haven't done stuff for like x squared or quadratic factors, and there's just slight differences in how you'll want to set up a, b, and c, and how to write out the different pieces. They have slightly different forms, but we'll do that in another video. This was already getting kind of long, but if you are asleep by now, I hope that you are having sweet, sweet, sweet dreams, and maybe you'll wake up knowing how to do this stuff, or feeling like, hey, maybe I had a mathy dream. But thanks for hanging out with me, and I hope that this was helpful. I'll try to add some timestamps here, but if you want to do specific practice and more of it, we definitely can, because I kind of wanted to move through this just so that we could go over it together. But anyways, I will talk to you very soon for more math, and definitely the quadratic case, and I'll just kind of cover briefly what to do in those and when it's repeated.